Welcome everyone to this webinar. On behalf of the AXA Climate and the SWIFTT teams, we welcome you to this webinar about AI models in insect damage detection in European forests. Forests in Europe have been ravaged for years by the outbreaks of bark beetle. Climate change really affects forests, causing insects to breed more frequently. Surveys indicate that the bark beetle infestation is the single biggest risk perceived by European foresters. Insect outbreaks are one of the leading causes of forest loss globally, destroying 85 million hectares of forest, worth 15 billion every year. Thanks to the SWIFTT project, which is financed by the Horizon Europe program, a consortium came together, including the present speakers, to create a software to face this risk and two others, namely fire and windthrow. Today is the first of a series of 3 webinars delivered in the context of the SWIFTT project and is going to focus on bark beetles. But as I said, the SWIFTT project also focuses on 2 other risks. This project's mission is to provide a scientifically sound and feasible way to help monitor and manage forest risks, windthrow, insects, and fire. SWIFTT, its ambition is to enable forest managers to adapt to climate change with affordable, simple, and effective remote sensing tools backed by Copernicus satellite imagery and powerful machine learning models. The webinar today will showcase the challenges and opportunities of artificial intelligence-based remote sensing methods for mapping bark beetle outbreak damage in satellite images by exploring the crucial role of field data collection to provide the requested effective supervision and accurate model development. The talks will highlight how collaboration between AI model developers and foresters is crucial to achieve accurate results in model development and maintenance. Today, we're going to be joined by our speakers, a mix of foresters and scientists, namely Juris Zariņš, head of the SIA Rīgas Meži Forest Management Planning Department, and Annalisa Appice, professor at the Department of Computer Science and Artificial Intelligence at the University of Bari in Italy. Juris, I will leave you the floor for your presentation.
I'm Juris Zariņš. I'm from Rīgas City Forests, that managing forest belonging to capital of Latvia. I'm head of Forest Management Planning Division, responsible for forest management, planning, remote sensing, and some scientific research issues in our company. So, in short, about the problems, about the bark beetle, spruce bark beetle damage. It starts, I think, some 10 years ago in Germany and in other countries. Actually, this bark beetle, it's everyday a problem in Latvian forests, but in a larger scale, it started some 10 years ago in Germany. So it's the forests all around Europe have growing pressure on the these insect outbreaks. It's not only spruce bark beetle, but we are starting with bark beetle because it's a main attractant here in Latvia. So and it's problematically to detect all the areas that is affected with this bark beetle. And only solution from our point of view, it's remote sensing that we can do and monitor it regularly. So, and thanks to climate change, these problems are growing. And no matter you are working as foresters in Central Europe, Northern Europe, or Eastern Europe, this bark beetle have no borders. As you can see, this picture from internet that I got border between German and Czech Republic. So it's different management activities. In one side, you can see it, all the damaged trees are left. In other side, all damaged trees are cut. Some I think, according to this young stand, some 5 or 6 years ago. So that's why in this project we are different foresters from different countries, from Western Europe, from Central Europe, because these attractants are different, and the tool in this tool you can monitor not only spruce bark beetle. About this Ips typographus, it's a major threat for conifers. It infests trees under the bark, and it's more vulnerable is trees above about 14, 15 years ago. Young trees, with young trees, it's no problem. Problem is that trees, the symptoms that can foresters see, you can view at times after that bark beetle, it's under the bark of a tree. And the reproduction varies each year. In some years, it's 2 times they are flying out from to next compartments. In last years in Latvia, that was 3 times. That is in previous years, previous 10 years, it's was it just 1 or 2 times that are flying out. So you need this monitoring system that you can monitor each forest stand minimum twice per year. And if you have a bigger forest area, forest property, it's impossible to do. So you need this remote sensing tools. And you need it fast, and to get information in the first stage, because if you are late with your decision in the forest, then would assortment lose half of price if you cut it down in just a few months. So just short about Latvian statistic, you can see it. It's a major problem in Latvia. On the right side is just interpolation of bark beetle damage in spruce stands in 2022. On the left side, you can see the flying activity. It's from Latvian Forest Research Institute, Silova research projects. So it's you can see it's not everywhere. So that's why the remote sensing monitoring system is best one, and this Sentinel-2 image that covers and you can cover large area of forest in one time. It's best one from our opinion. Just short about our statistics. Today we are talking about bark beetle problem, but in next webinars will be information about the wind damage here in Latvia as well. So on the left side you can see it all forest compartments near the Riga. You can see the red one. That is somehow damaged in the last 10 years. So it's major problems, and we need this remote sensing solution for our everyday activities. Just short about national activities, how we deal with this bark beetle before. In the last 3 years, I guess it's we have so-called bark beetle emergency plan. So in Latvia we have a state forest register, and you can choose the spruce stands that is valuable one, and around this spruce stands, on the right side of presentation, you can see that this buffer zones. So in these buffer zones, in the spring and summertime, it is cutting restriction activity, cutting activities restrictions. So you cannot cut forest without special permission from State Forest Service. Other activities is to place we're placing pheromone traps in the forests, so trying to attract this bark beetle from the spruce stands, not to damage them. So we have information how big it is this flying activities, how many bark beetles we are catching, and providing this data for state authorities and for researchers here in Latvia. And in Latvia, it's I think 2 times we are getting 1 time Earth observation assessment of affected areas for whole of Latvia's spruce stands, but it's one time, and that was some 1 year ago, and you can see it in the State Forest Register. In the left side, this damaged areas. So, but as I said before, we need this monitoring tool twice per year, and it's not enough just once a year to make such estimation and get a result from that. And the case study, how we are participating in this project, we are a municipality-owned forest company. We are managing about 62,000 hectares near the Riga, and some small forestry a little bit north from Riga. So, and we have a lot of this bark beetle outbreaks in spruce stands in last 2 years. In last year, in 1 quarter, assortment amount that comes from this affected areas was 1/2 of all the assortments that we are cutting. That was huge amount of damaged areas. And this challenge, what we are facing, visual symptoms appear late. So field surveys, we cannot cover all the spruce stands twice per year. It's slow and costly. And sometimes detection comes often too late to prevent spread, and we losing valuable for timber assortments that we are not getting information in time. And we need to quickly recognition. We need quick recognition of the territories of affected territories, and one information that we get from our project, it's very difficult to catch the first stage of insect outbreaks in forests. Previous activities that we done in our company, we done first risk analysis mapping. It's according to spruce stands above the diameter, I think 30 centimeters. So we are mapping all the spruce stands, and this is areas where the foresters need to get and make the monitoring first. We are surveying the territories that is under this risk analysis mapping, and only that we can do, it's do the selective sanitary felling in sanitary clear felling to fight with this bark beetle. And of course, we are placing pheromone trap we have collaboration with scientists giving all this information, all the stands, and one collaboration with the scientists is this project. Earth observation practice at Riga City Forests. mainly that we can do it with our drones. We are flying with our or about 14 drones that we can fly, and to make some photo imagery, find damaged areas. But as I had said, you cannot cover all the area, because you know that drones you can fly here in Latvia just on the visibility distance. So other thing that we are trying is to use Sentinel 2 RGB imagery. It's just to add at the background of our forest digital map. And we are trying to make some NDVI index to detect drought or bark beetle impact. But once again, this is one-time activities, and that activities can do just specialists of remote sensing, not ordinary foresters. So that's why we need this monitoring tool. And one time we are also outsourcing Earth observation from outside, just giving this our risk analysis map some areas. Maybe they can get some information from satellite imagery. But again, it's one-time activities, and better is to make some tool that is independent of remote sensing specialist knowledge, and that can just use ordinary foresters. And about using drones, we are using just this RGB imagery. We are trying some 3 years ago drones with spectral cameras, but once again, you can cover maximum 20-30 hectare area. Then you need to make photo imagery. Then you need to estimate is it damaged areas or not. So yeah, it's not coverable with drone activities. On the right side, you can see the problem that we have. This all white areas, it's sort of photo imagery from winter time, but all these white areas was affected by bark beetle, and then we are going taking it out, and after some half of years we are getting in this area again and getting new timber again out. So yeah, it's a widespread problem here in Latvia. About the collaboration with researchers, the main challenge that we try to solve in this project is to get this early detection when the timber quality is high, but bark beetle is in the forest. And this is best time when we need to cut forest and get out, not to lose quality and value of assortments. And we need to try and this accurate predictive models. Why we are cooperating in this project? Because we have got a wider data set, because we get data from Germany, from France, and other thing, we got experience with other pests, insects in context of climate change, because we are a little bit norther, but we are getting new attractants here in Latvia from south. And yes, we can get experience from other countries how to detect other pests, insects that we are facing, I think, in next years. And we need system that is not just statistic. This system that continues to learn from data. So I think in next webinars, colleagues are showing how with an app that is in mobile phone, we can help the system to develop further. And the system uses this field observations. We have do a lot of field observations in our forest to ensure that this system works for us and to detect that what we need. And just some takeaways from that from our problems. Yeah, I think the insect outbreaks are intensifying, and it's hard to see and predict with ordinary methods. Early detection preserves forest and economic value because we can get these assortments as soon as maybe after the first stage of impact of this bark beetle. And remote sensing enables smarter response, and with these tools can work not just remote sensing specialist, but can work ordinary forester. They can use it in a mobile phone. So, and we hope that this practical model can get for us regular monitoring with help of Earth observation technology. So that's in short from my side. Thank you for attention.
And thank you, Juris, for the introduction to our work. I just would spend a few words about the team, and after that I will move immediately on the main topic. The team working in the project is composed by some tenure researchers of the KDDA laboratory and the University of Bari, and two very good non-tenure collaborators that performed fantastic technical and research work. We are a scientific lab in the university. We have skills in teaching and research, mainly for artificial intelligence. And our personal story with bark beetles started with the SWIFTT project, where we were involved as a research institute. So mainly for our research activity that was mainly devoted to investigate how artificial intelligence technique may be used to process Sentinel-2 data collected with the Copernicus program to develop AI models that may help foresters in their monitoring work of the bark beetle outbreak. The tasks from the scientific point of view that we addressed are several, starting from data engineering, because data must be represented and processed in some way to understand which kind of data we can analyze, if we need one sensor, multi-sensor imagery data, if we have to focus on one shot snapshot or several snapshots in time, so time series of data. From the methodological point of view, we explored the machine learning and deep learning architectures, also depending on the type of data that we have. And more importantly, and this is very consistent with our expertise in Bari, that is very strong in symbiotic AI approaches to problems, we worked according to a data-centric AI approach. So we started from the data. So the data are not the end of the process, but the real beginning. And we worked a lot paying attention to obtain high-quality data because they are the real factor of success for artificial intelligence. And for this, the collaboration of the forester was really crucial, and we were lucky because we found a very good partner in this project for this collaboration. First of all, because they have to clarify out what they need and what they expect for us, because we are not experts of forest, so their help is crucial for this. And they share their knowledge about the forest life and what is the real forest danger risk. So their knowledge on the domain was the starting point for performing a good work with artificial intelligence. The last point is the most sensitive because they helped us in developing AI techniques because they provided the field data. Sentinel-2 data may be downloaded, but the map of the outbreak they can be provided only by the foresters, and these are necessary for the supervision of the AI methods, because AI methods cannot learn without appropriate supervision. The consequence of this good collaboration is the possibility of designing AI tools that use machine learning and deep learning advanced technique that trained on labeled data can be eventually used on new areas of the Latvia forest, in this case, to map bark beetle outbreaks. Clearly, the final goal is that of offering a tool that can help foresters in continuous monitoring, trying to reduce the workload. But again, we cannot replace humans. The humans are in the center of the process, and without them, we cannot achieve any good result. The data that we used are the Sentinel-2 data, because this is in the asset of the project, and also because they provide continuous pictures of the Earth. They are collected every few days and cover almost over the Earth's surface. They are obtained with a multispectral satellite that collects several bands, providing a different kind of information. And staying at the literature, these information are very useful for exploring chlorophyll degradation. For example, green, red, and near bands are very useful for this analysis, or exploring some loss in vitality. For example, these veer bands are very useful for this kind of analysis. And finally, there are the red edge bands that are very important because they can show some symptoms of insect presence. More importantly, these bands are collected at different spatial resolution, but the lowest one is at 10 square meters. They are open science data, so they are free available for everyone thanks to the Copernicus program. They can be easily downloaded by using some Google Earth Engine APIs. That is what we did within the project. And they are periodically acquired, so we can count on continuous Sentinel-2 images with some problems due to cloudy and so on, but they continuous monitoring, continuous observe the Earth. In addition to the spectral bands that are not collected with the Sentinel-2 sensors, we consider additional engineered information that are extracted from the spectral bands. They are the spectral vegetation indexes, and NDVY that was cited by Juris is one of the spectral vegetation index that is commonly used to monitor the health status of the forest. But in our preliminary recognition, we identified more than 40 indexes that were commonly used by researchers and technicians that work with the bark beetle outbreak detection. So we explored how these indexes may be used to corroborate the analysis that was performed based on the Sentinel-2 data. Here, just an example of some of the indexes that we considered. And it's a simple picture of an outbreak detected in some historical data in France. And we can see how some of these indexes, for example, NGDRA, can help in correctly identifying the white zone that represent an example of outbreak. So from the data engineering point of view, our result is that, okay, Sentinel-2 data, but enriched with spectral vegetation indexes that can help us to better delineate the outbreak. Another important contribution, still staying in the data engineering phase, is that of handling with the spatial autocorrelation. This is an expected phenomenon. It is a consequence of the first law of geography. Everything is relating to everything else, but near things are more related than distant ones. If you think this is obvious thinking, because I can expect that close pixels measure similar values, but we have to take into account this. So for this reason, we don't focus on just values measured by spectral bands and indexes at specific pixels, but also considering this information in a spatial surrounding. Clearly, this is done synthesizing this information with different operators like the minimum, maximum, average, and so on. Again, in this picture, I showed as these spectral spatial features again can contribute to better delineate the information regarding the outbreak. About the approaches, we have a long experience with research in artificial intelligence, more than 20 years, developed in different projects and working in various tasks. And staying to our experience, we explored both unsupervised learning and supervised learning. Unsupervised learning means spatial clustering, change detection, saliency detection. From the forest's point of view, this is very nice because it means no need of labels, so no effort from their side. Because we just work with the Sentinel-2 images, in this case, without any supervision. And if we have labels, they are just used for evaluating the goodness of the methods. On the other side, the supervised learning approach, pixel-wise classification or semantic segmentation, require labels. Without labels, we cannot train any supervised models. But the effort that is required in collecting labels is balanced by significantly higher accuracy. We explored the difference in some literature data that are available online for historical data on the Czech Republic, and this is a simple example. We passed from 58% of F-score to 72% of F-score. For this reason, in the SWIFTT project, we moved definitely, after some investigation, on the use of supervised learning, thanks also to the collaboration of foresters that provided us the labels of supervision. Moving on the methodological point, we explored both machine learning and deep learning methods. The main difference is that in the machine learning case, feature engineering a priori, outside the learning method, that is just focused on learning models. In this case, machine learning methods can be used for pixel-wise classification. That means we train a model that labels each pixel by considering the information collected in the current pixels. Clearly, the features are constructed manually. On the other side, in the case of deep learning methods, we can use deep learning for training a classification model, but also semantic segmentation model that are very strong because they isolate object within a chain. So the outbreak is separated by the earthy surrounding. The advantage of deep learning architecture is that no feature engineering is required a priori because the network itself is able to perform the feature engineering step. For the machine learning, we explored the different models trained with random forest, XGBoost, support vector machine, multi-layer perceptron. And as we have a problem with data imbalance, because outbreak is very spread, but the earthy forest is a bigger amount of earthy forest than damaged forest. So the domain is typically imbalanced. Use some approach, like cost-based approaches, to handle with this data imbalance. This is from the technical point of view. On the deep learning, we explored the different architecture, like convolutional neural network, large language model for pixel-wise classification, and mainly UNET for semantic segmentation, using a weighting schema or ad hoc losses for handling the data imbalance. So the difference that defined our decision of moving at the end of pixel-wise classification is the requirement for the labeling phase. Because for developing a pixel-wise classification model, we just need information on polygons that are damaged or polygons that are earthy, without requiring any information on what is in the surrounding of the damaged polygon. So we can use the polygons ignoring completely what is in the surrounding. While if we want to use a deep learning for semantic segmentation, we need to start with a completely annotated map where we have information on each pixel. So we need to understand where the polygon is damaged and to know exactly what is in the surrounding. Clearly, from the field collection side, obtaining labels for a completely annotated chain is more time consuming. And clearly this requires a burden of work from the field work. Some guidelines that we have identified for the collection of the ground truth. First of all, we need both damaged and healthy polygons. So we cannot work with just example of damaged polygons because we need to show the difference, because the system must learn the difference between the two different types of forest. In addition, the polygons must be accurate. So they have to really delimit a damaged area or an healthy area, no mixed areas. Polygons must be acquired with metadata. So we need to understand when they are acquired, in which stage the outbreak is, when the outbreak started, and have some information on the history, how the outbreak evolved over time. These timestamp information are required because the forester provides us the map of outbreaks for the supervision. But we have to download the Sentinel-2 images, and we need to know when we have to download these Sentinel-2 images. So it's crucial to have this time-stamped information. Here, just an example of how we can pass from the map of the outbreak provided by the forester to the imagery dataset that we use for the artificial intelligence supervision. They provide example of polygons labeled with damaged or healthy. We construct a bounding box that surrounds the polygon. Using the bounding box, we query the catalog of Copernicus images with a specific timestamp corresponding to the period where we know that the area is damaged or healthy. And we download images for which we can construct a map of the labels. In this example, black means that each pixel in the same area is damaged. What we can do to collect this field data? At the beginning, we started with the idea that we can use what is already recorded by the foresters, so their historical data. The problem is that the collection wasn't performed according to what is expected for developing an artificial intelligence model. It was collected for their recording scope. So in a majority of cases, foresters collect only damaged polygons. They don't collect all the information on the timeline. They just collect information on when the polygon should be cut. And this is the most important problem. In the majority of cases, they record sanitary cuts. That means the area that was cut to remove the outbreak and prevent the diffusion of future outbreak in near zone. The problem of the sanitary cut is that they cover area that is damaged, but also surrounding area that is not damaged. So, and we are unable to distinguish the damaged area from the healthy area within the same sanitary cut. This is just an example. We have a picture of a sanitary cut happening between May and June. We collected a picture. This is the RGB representation of the Sentinel-2 images. And we can see that the sanitary cut was there. But the damage is not spread on all the sanitary cut. It is only in a subspace of this sanitary cut. But we haven't this information. So when we try to use the sanitary cut as outbreak maps, we created that with a lot of hallucinations for the artificial intelligence model. We did the experience because this is the lessons learned. So we started using sanitary cut for creating our imaginary dataset. Sanitary cuts were provided by our Rīgas Meži partner within the project. And when we created the imagery dataset based on the sanitary cut and trained our model for classifying pixels in healthy and damaged, according to the theory that we have developed in our project, what we obtained is an F score of 52%. That is not very good, with a lot of false alert. But if we consider all the problems with the sanitary cut, this result is obvious, because we supervised our model showing a lot of pixels that were labeled as damaged, just because they were cut, but they contain trees that are still healthy in the corresponding Sentinel-2 images. This is the example of hallucination that was created with the artificial intelligence models. So what we did in the project is thanks to the application that was developed by our partner Team Tract, the foresters of Rīgas Meži were able to go in the forest and perfectly annotate the polygons representing the outbreaks, collecting all the requested metadata that we defined with our field collection protocol. And according to all this information, and also the polygons of the LT area clearly, according to this information, we were able to create the query for the Copernicus systems using perfect polygons and not sanitary cut with hallucination. We created a new imagery dataset that is composed by Sentinel-2 images labeled with the map of outbreak and LT areas that reflect the real situation in Latvia, and train our model. Clearly, for the evaluation, we separated the polygons in training and testing because we needed to perform our evaluation in a safe way. So polygons used for training are never considered for testing and vice versa. This is a map of where training and testing polygons were spread. And when we constructed our model and tested in this situation, we passed from the 52% obtained with the sanitary cut to the 72% obtained with the real outbreak polygons acquired within the project. So this is a picture of some of the prediction map that we have constructed, and this is a map in detail. We have the map of the outbreak as it was detected in the several months of 2024. Consider that these data were collected in February, so refer to outbreak occurred in the previous year. So our lessons learned from this big collaboration is that clearly the role of foresters is crucial, because if they don't provide us the correct maps to create the imagery dataset for the supervision, we cannot do too much with our artificial intelligence tool. What we are doing now is continuing with the field data collection, because this is just a first experiment, but we need to create a greater dataset for better developing and testing the models, and also acquiring data in different areas, because the transferability from one geographic area to another one is not so trivial. We need labels acquired in different parts of Europe if we want a model that works in different parts of Europe. I conclude here. I just want to give a track of our research work done in the project with the list of publications where we have described some of the results described in this webinar. And thank you for your attention.
Thank you everyone for your participation today. And we look forward to seeing you at the next webinar.